Okay, so we continue with our previous class, and where we discussed about the various transistor networks, and in that case, we talk about NMOS transistor, we talk about PMOS transistor, and now we are talking about the pass transistor. We call them a pass transistor. Why? Because we see that when we apply input to the terminal of these transistors, and when we have a control over the gate, they act as switch, and therefore we say that we can have NMOS as a switch, PMOS as a switch. But there is some issue. What I want to understand you that what I want you to understand is that we know that NMOS passes strong zero but degraded ones. What does that mean? So let's say we have this NMOS transistor over here, and we have a control in the over the gate, and we have an input here that wants to reach at the output. So input can be 0 or 1, and accordingly it will reach 0 or 1 when the gate is enabled. Right here is the control. So just remember now, NMOS passes strong 0. So if the gate is enabled, the transistor is switched on, the 0 can come from A to B, and we say that NMOS passes strong 0. Okay, but the PMOS, okay, but for what about the 1? So when we apply a 1 at the input, and when the gate is active, transistor is switched on, we see that NMOS passes poor 1, or in other words we say that degraded 1. Now what is the meaning of this one? Degraded means essentially we are having 0 or 1 as a data input, okay, and on the gate we have a control. We are dealing with the logics 0 and 1, so we have this one. And when we implement this network through the power supply units, we have a VDD and we have a ground. So these two power rails, these are called as power rails. Essentially they are the strongest signal sources, right? So when we say that output is, we apply input to a circuit, and the digital circuit switches between 0 and 1. So what that does mean, essentially that means these power levels, which is VDD is nothing but high logic and ground is nothing but low logic. So this power level logic is thrown to the output. In other words, we say that output gets connected to either VDD or ground, or logic high and logic low. So it means they are the strongest voltage sources, either 0 volt or 5 volt, or just say high and low. But when we use NMOS as a transistor, and we have to pass 0 or 1, so just for now remember, NMOS is known to pass strong 0, but it is known to pass degraded 1. It means the degraded means VDD should be level at the output, or high should be level, but it will be somewhat below the VDD. So if it is 1 volt, we'll have about 0.8 volt or zero 0.9 volt. So we'll say that it is a degraded one. We'll see that in detail later. Similarly for the PMOS. So for the PMOS, we want to make another statement. What is that statement? We have PMOS transistor here. It has A input and it goes to output B, another end B, when we have a gate control over it. So when the transistor is switched on, A could be 0 or 1 and it reaches 0 or 1. But for a PMOS, we'll say that PMOS passes strong ones. So it's a very good switch to pass 1 from A to B. But we'll say that it is not that good switch to pass logic 0 from A to B. So it means we want ground at the output, or logic low, right? This is what. But somewhat the voltage level would be somewhat above the ground level. So if it is 0 volt, so I will have 0.1 volt or 0.2 volt, just similar to this case. So that's why we come up with another switch. So we say that we combine NMOS and PMOS in parallel to each other. So we see this, we call it as a pass gate. Okay, and we have also called it as a transmission gate. So what happens, this drawback of NMOS and PMOS, we say that A can be a 0 or 1 logic, B will have 0 on 1 logic when this transmission gate is active or switched on. So when let's say G equal to 1, it means GB equal to 0, because they are the complementary logic. So this transistor switched on because it's a combination of NMOS and PMOS, and whatever the logic level comes at A, that appears or that passes through the switch to the logic to the level B. Okay, so this is what we'll say that. So again, the transmission gate, to conclude, is known to pass both strong 0 and strong 1. In case of some logic, if you want to pass only logic 0 from point A to B, okay, then use NMOS switch. If you want to pass only logic 1, then you can use PMOS as a switch. You don't need a transmission gate. So this is just a basic, remember, when we will talk about switches, NMOS, PMOS and the pass gate. Pass gate is known to pass or transmit logic low and high at a strong level. So for instance, we have seen that in the case of inverter. Okay, we'll see that in the next slide.
So are we going to study later that why that output is degraded 1 in NMOS?
Yeah, we are going to study that, right? We are going to study that here in these slides only. So non-inverting logic gates, we are talking now about non-inverting logic gates. So we have talked about inverting logic gates, right? Inverting logic gates.
Yes.
So inverting logic gates, we know that the output function is nothing but a complement of input, which is nothing, a classic example of NOT gate, or we call it as an inverter, right? We also know that Y equal to A and B bar, so we call it as a NAND gate, 2 input NAND gate. We also realize that A or B, we call it as a NOR gate, right? But then some question came also, how to realize non-inverting functions such as Y equal to A, we call it as simply non-inverting, then is the inverse of the non-inverting. So we will see why we call it as a buffer also. We've seen that. So we just want this function Y equal to A. Then suppose we want to realize this function A dot B, not the bar. So we know that this is basically AND gate, AND logic. If suppose we want to realize this function Y equals to A or B, okay, so we know that this is OR logic, and I have told you that to implement these logics, so for instance I know that inverter circuit is like this. Look at this circuit. We know that we have a NMOS here and we have a PMOS here, and then I have a VDD here and I have a ground, and then what I do is that here is the output, which is the complement of the input. Simple. So how this works, we know. So when the logic A, whatever the logic is at A, 0 or 1, Y would be the complement of that. How? At a particular time when I have a logic 0 at the input, upper transistor will get on and the bottom transistor will be switched off. So I will say that this logic level, which is high, will be thrown through the output. When input is at 1, bottom transistor is switched on, PMOS is switched off, and I know that this logic low level is thrown at the output, right? So what I'm saying that VDD again and the ground, these are called as power rails. They are a good voltage sources of throwing the logics at the output, logic 0 or logic 1. But okay, so we have just made a statement that both NMOS and PMOS transistors produce degraded outputs. It means NMOS is poor at producing strong 1 at the output, and PMOS is not as good as producing strong 0 at the output. So what about I want to implement this function Y equals to A. So can I just think of just swapping the position of these two transistors in the bottom figure and create this structure? Why not? Let's say I have an input A. What I did here, PMOS I took at the bottom. So now pull down network got below, and NMOS I took up. Can you see the similarity or just a small difference between this circuit and this circuit? Right? We can see that. So I just swapped the position of this transistor. Now tell me the working of this transistor circuit. And the question would be, is it a good design? What I can see is that, okay, A can be at the logic 0 or 1, and accordingly I can have Y equal to 0 or 1. How? Can you see that? A is at the logic 0, it means bottom transistor is switched on and the Y is connected to logic 0. So it is this one. When A is equal to 1, upper transistor is switched on, bottom is switched off, and Y got connected to VDD. So whatever the appears at A, based on the combination, I get Y equal to A, not the A bar. Okay. So this is how I am able to invert, not invert. I am going to create a non-inverting function. So I know that this is a circuit to create this function, and this is a circuit to create this function. But now question is it a good design? If yes, how and why? If not, why? Anybody?
I don't think it is a good design because I have never seen this design.
Yeah, but just because we haven't seen this design, therefore can we declare, okay, this is not a good design because we haven't seen that? But I say yes, you can implement this way also. Why not? Because I am getting Y equals to A. Okay, so again that question comes here. Remember this, VDD and the ground are the two good voltage sources, and actually these are the logic levels that we are looking at. VDD equals to high, VDD is high and the ground is low, right? So what we see here, if you see the operation, PMOS when switched on, it is now throwing the logic 0 to the output as opposed to our earlier convention. We have always seen that so far in all lectures, NMOS was the pull down network that was responsible to connect or throw the logic low level or ground signal to the output when it's switched on. And we know that the PMOS transistor was in the pull up network, and that was responsible to connect our output to the VDD logic high. But now we are just doing the opposite, and we have declared that PMOS cannot be used to have a strong 0 and NMOS cannot be used to have a strong 1. So that's why we will say that even though we are constructing and designing this circuit, what we may face in the output is that when A in the truth table, so this is logic 0 and this is logic 1, so we'll have a 0 here, but it could be a degraded 0, and if it is 1, it would be degraded 1. Okay, so 0 is coming because of the PMOS here, just opposite to earlier case, like this is the inverter in the bottom, and 1 is coming at the output because of the NMOS. And we have just declared the two rules that NMOS is only good for passing strong 0 and PMOS is only good for passing strong 1. That means strong 0 is strong low logic and strong 1 means strong high logic. So we'll see that in subsequent classes in detail why. So we've just seen that this is not a good design, you should avoid it. So then question is how to create such non-inverting logic gates. I just told you that we want to create all these logic gates. We know that NAND, NOR, we have created an inverter also. We know how to know that. But what about these gates? What about these gates now? Or AND or just Y equals to A. This is the function. So simply don't go for such design. So what to do now? Such technique should be avoided. So what to do now? We'll just make we'll just make a NAND gate, whatever, and just invert the function. It's simple, as good as that. Simply. Again, you have this, let's say, NOR logic and put the inverter function A and B.
Sir, this design, so still we can use the design, sir.
You can use this design, but like I said, you output, look at the outputs what we have seen. When you have a 0 is coming at the output or 1 is coming at the output, that's okay, you are getting that, but it may be like this. The output, this is VDD.
Yeah, degraded will get it, but still the performance may be less. But still, if you want, you can use it.
Yeah, you can use it, but people don't use it because you want a strong signals, right?
Okay.
So again, we are continuing with these logic gates, non-inverting logic gates. So for instance, I am now talking about how to create some other functions. For instance, I want to build a non-inverting functions for multiple stages of inverting gates. So just I want to make this AND function right over here, AND logic. So I know that I have these 4 inputs. We have seen that in previous class also. So there are ways, but you'll see now there are always 2 levels. So I'll have to invert the signals. I can't really swap the pull up and pull down network and go for it. So first way is that I will use this I will use this NAND functions and then just use, this is called as bubbled NOT gate or bubbled inverter, simply say that. Another function is that, another function I will use 4 inverters first and then I will, this is called as bubbled AND logic. Okay, and then
is it AND gate or it should be a OR gate?
Which one?
So this the one second logic as per Demarcus law, I think it should be an OR gate.
Why and how?
I saw in your slide when we are doing using bubble, it was converting from AND to OR.
Yeah. You can verify that operation also, but just these are the ways of implementing those functions. That's possible. Yeah. And the third case is just split the 4 inputs in this case and then use such logic. So I have just made a comment last time that each of these design, they have different speed, size and power. So it means in each of the logic gates we know that how many transistors are used. For instance, for inverter, how many transistors we have? 2 transistors. And then for this gate we know the how to make the transistor level implementation of this. Can anybody tell me how many transistors?
4 plus 1.
For the NAND.
2. NAND 4.
Yeah. So you can just go back to earlier classes and earlier slides and see that how many gates in each of the logic is going to be there, and based on that you can estimate the size And then speed also, speed as we have commented before also, speed depends on the transistor logic switching and how many levels are there, but there are two levels now, we've seen that in each of these configuration. So speed is really a matter of research, we need to inspect that. Power also, again you have to compute and estimate. So tools are there, they will give you the clock, at what clock, maximum clock each of these circuit can run, and what is the power consumption based on your implementation. So now let's take a look at this concept in more detail that we've got previously. I told you that there are three states. So far we've seen two states only, logic 0 and logic 1. And there is another state that we are going to define, that is called as high impedance, or simply say Z. Okay, so first, when we talk about two functions now, this is first function, y equals a invert a bar. It means whatever the input is at a, that y will be a complement of that. And there is another function, we just see that y equals a. So we know how to implement this function. It's nothing but a NOT gate, an inverter. And what about this function? We can just have such implementation. Is it correct?
Yes, sir.
Right. So there is another way to do that. So we'll see that also. So first is, we call it as a buffer. Okay. So buffer has a symbol like this. So you see the difference. Don't get me confused with the symbols of inverters and the symbol of this tristate buffer. When I say tristate inverter, it has a way to show the symbols and the circuit. And when I say tristate buffer, it will also have the way to show the symbol and the circuit. And we'll also see the minute difference, a little difference between these two. So first let us take a look at this tristate buffer, how it works again. So symbol is that you have input A, you have output Y, and there is one extra signal needed here that we call as an enable. So this signal can be generated inside the cell when you write the code. Okay. Another way is that symbol, you have input A, you have output Y, and the control input, or let's say enable input EN, along with its complementary, can be shown in the symbol. So just I will show EN here, I will take EN bar and I will just put a bubble here. So it shows that this is the complementary of EN. It's very simple. And what I see that how this circuit will work, when the enable input is 1, the output connects to input. Simple. So A has 0 or 1, it will reach to output. That is very simple. And we have seen that transmission gate also. It is a truth table of this tristate buffer. So see again, enable or enable bar, whatever the case you say that. When enable is 0, it means I am disabling this gate. No output will be not logic or not logic 1, rather I would say the output is floating. I call this state as a high impedance C. So when somebody asks you what is tristate buffer, you just tell them that when enable is disabled, output is floating and the gate is set to be in the high impedance state. However, when enable is 1, whatever the input is there, 0 or 1, that gets connected to the output. Okay. So this is the working of. Now the transmission gate also, and transmission gate is also having the same truth table function. Again you have enable, and with this bottom representation I show its complementary function. So when I
Sir, never. The input and output are same for the buffer. Then what purpose we are using this buffer?
Input and output are the same in the sense that sometimes you have multiple networks that wants to have access to a common bus. Just like in the multiplexer that we have seen yesterday, you have many inputs, and at a time based on our control we connect that input to the output. So for instance, you have inside the chip you have a bus and you want to have a particular cell wants to have access to that bus. So we can choose out of n number of functions, which function will have access to that bus. Okay.
Okay, sir.
So transmission gate, this is also the same truth table, and we call it as a non-restoring circuit now. Can anybody tell me this transmission gate, or let's say this buffer, why we are calling it as a non-restoring circuit? So non-restoring circuit in the sense that, you see, this logic level at the input is coming at the output when the transistor switch is on. This transmission gate switch is on. What about the inverter? Let's say this is just a short here. So it's the very same inverter that we have been seeing. So what we see that when there is a logic present at the input, the power level comes at the output. Not the input is transferring to the output. Not the input is passing to the output. Just see and try to understand the difference. Again, transmission gate or a pass gate has a property. When we switch on this switch, whatever the logic is at the input, that gets passed or transferred. That's why we call it a pass gate to the output. But in case of the logic gates, when the input is available, it makes the switches on or off, and based on that condition, the power rails gets connected, or the level logic high or logic low gets thrown at the output. So it is called as restoring logic gate. This is called a non-restoring circuit. So remember, in non-restoring logic or non-restoring circuit, the inputs gets connected to the output, and in restoring logic, power rails throw the logic levels at the output. And what is the beneficial? We always want a strong voltage sources, or 0 or 1. We don't want degraded outputs. That's what we have discussed so far. So we'll see that how to create this restoring logic gates. So this was for tri-state buffer. Again, what about we want to create a tri-state inverter? Now I want y equals to a bar. So again, I just take 2 transistor up, 2 transistor bottom. So just have a look at this circuit diagram. I have input A, output Y is here, and I have enable a single signal and its complementary En bar. So when En is equal to 0, the circuit is switched off. Look at this. Can anybody tell me what comes at the output, logic 0 or logic 1?
It acts as an inverter.
No, it's not acting as an inverter. Let's say enable is 0.
Enable is 0. It is acting as a
PMC circuit.
When enable is 0, this transistor is switched on.
circuit.
This transistor is switched off.
Impedance.
High impedance, right? So in case of inverter, we have
Yeah.
in case of inverter we have only 2 states, but now this is special case, tri-state inverter. So we have 3 states. So we'll say that output is floating because you see both switches are off. So I have a special control here in this circuit. But now when the enable is 1, so I will have this configuration. So it takes my very simple inverter, what we can say that, and now this output is actively getting driven by the supply rails, either VDD, logic high, or logic 0. So that is how this inverter will work, and it is a special case tri-state inverter, and it is a restoring logic. Why? Because output gets driven by the supply rails, not by the input. What is the symbol of the inverter? Just show a bubble here. See the difference now between the buffer y equals to a enable. Again you have a control here enable, but you have an inverter bubble here. When you want to show the complementary here, this one again and this one here, just put the bubble and it becomes tri-state inverter. If you remove the bubble, it is tri-state buffer. So now we want to yesterday we've seen that inverting multiplexer. So there are two ways to construct this logic. We've seen that, and somebody asked me, I said that one approach is using compound gates. Just remember this, compound gates. Just before that, I want to pass on one information. In the interview you might be asked the question, what is tristate in CMOS logic? You can note down this question, very common question they ask in the interview, what is tristate logic? And on the next question or followed question could be, tell the difference between tristate, buffer or inverter. The follow-up question would again be, draw the circuit of tristate logic. Follow-up question could be, draw the truth table of the tristate logic. So inverting multiplexer, I told you that. So there are two approach. First is using compound gates. Compound gates in the sense, just have a pull down network, just have a pull up network, and you have a VDD here. Let me draw. This is your VDD and this is your ground. Okay, and what I see the configuration, okay, two inputs. This is two input multiplexer where data inputs are 0, D0 and D1, right? Just remember this, D0 and D1. And I have a control or say enable. So there are so many words I am using here. I can use control or I would say enable. Enable, and it's complementary. So usually I would say control when I'm using them as to make them on and off, and I will use this enable and it's complementary when I'm trying to make the whole circuit on and off, right? And control would be just for single transistors, and MOS, PMOS are just a pass gate. So you can use any word, no matter, just say enable or control. Because we'll see that these will be driven by the clocks. The clock goes on and off, and accordingly this network gets on, switched on and switched off. So this is the 2:1 multiplexer. D0 and D1 are the data inputs, and output, it is called as inverting because we have shown a bubble here. If I don't show a bubble here, I would say it's a simple multiplexer. Okay. But now I am calling it inverting multiplexer. So do you see now what is the output function and what is the relation between output function and this network? Does it make sense?
Yes, sir.
Right? Can I write y equals to a bar d naught or a d1? So it's just like S bar and D naught or S and D1, right? So D0 and S bar output can have the value of D0 when you can just apply 1 or 0 here. Let's say S equal to 0, it means S bar will be 1. If S equal to 1, then S bar will be 0. So simply just apply this logic, and based on that we see here now, if S equal to 0, just come here to this network and see that which transistors are on and off, and we see that I am able to pass or connect D0 to the output. 0 will get to Y and 1 will get to Y. No matter at that time what is the condition on D1. Okay, so is it a restoring network or non-restoring network? I just explained you. Multiplexer, what is the function? What is multiplexer doing here? It's just a data transmission circuit, right? It's just connecting data from input to output. D0 to Y or D1 to Y, right?
Yes, sir.
So it's a restoring or non-restoring? Does the logic level at the Y
It
coming
is
from
restoring.
the restoring?
Yeah, which is connected to, which is no, not provide the input, which just provides that no power high or low. I think you said that is called restore.
Don't get, yeah. So once again, is the logic level at the output, logic level is high or low? Is that logic level at the output coming from power rails or the input data?
Power rails.
No. We are saying is the input gets Y gets connected to D0 when S equal to 0, when the control is 0.
Yes.
So output gets connected to the inputs D0 and D1, either D0 or, see the OR function, or D1 based on the control inputs. Simple. So it's a non-restoring network. And is this a good way? We'll see that this circuit is good, circuit can work, but VLSI designers, engineers go for strong logic networks. So we want strong output levels, VDD, not the degraded and the ground. Here we'll see that the output, the logic level high or low is thrown by the supply rails, not the D0 and D1. We'll see how. So again the truth table, let's complete the truth table. When S equal to 1 here, it means S bar equal to 0. When I'll say S equal to 1, we have to assume that its complementary will be there. So doesn't matter what is at the D0, this D1 data goes to output, simple. So this is the one way of implementation. Now second circuit. So what I do is that I take two tri-state buffers. Just see the initial circuit. I have A, so instead of A now I will say this is for one D0, and I will take one such network again and I will call that D1. So similar, I just done that, D0 and D1, and instead of enable, here I have S and S bar. So instead of enable and enable bar, right? So what do you see here? See the slide arrangement. Can you just see now or try to understand what changes from the top circuit, what changes in the top circuit I made to come up at the bottom circuit? Just have a close look at both of these circuits and you should be see a little change I have done. Maybe just
NMOS one pair was there parallel in the above. Below pair of PMOS are in series.
Right. So what I see here, look, these two series NMOS and this two series here in NMOS. Right here, this two and this two, and there is a ground here. So what I can see that I have S and S bar control D0 and D1. So do you see that I am getting the same here, these two NMOS and these two NMOS, the ground is common here. So pull down network is same as this one. Any doubt? Again, once again, see D0, D1, S and S bar. So I have four switches here again. So I just turn their direction, they are facing each other. For example, the ground is common. So what are the conports? S bar, S, just like here, and D0, D1, they are coming from the top also. Just remove this line maybe here, and I have two D0 and D1. So it's just like four control lines, four input lines. So pull down network consisting NMOS transistor, they are same, right?
Yes, sir.
And now look at the top arrangement. Some changes here. So S and S bar, D0 and D1. So again I have S and S bar, D0 and D1, but some little change is there. So pull up network is little different. Just a proper misplacement of the transistor. So this is how I took two tri-states, and then output of the first tri-state I gave it to another tri-state. I connected in this way right at this node. And now again, how to analyze how the circuit will work? Again, put S equal to 0, it means S bar equal to 1. And for a simplification, you can draw this network at S equal to 0 and S equal to 1. How the switches will open and close, you can simply draw this. And accordingly, you can verify this truth table again. So when S equal will be 0, you will see that D0 is getting connected to output. Can we see that? But now we'll see D0 is getting connected to output for S equal to 0. It means the logic at the power rail is thrown at the output, unlike this case, because you will have this configuration. Are you following me?
Yes, sir.
Yeah. So these two approaches, people go for the bottom one, tri-state. Why? Because this is slightly compact. Can you see that? Pull down network is same, but we just arrange upper network a little bit modification, and because of that what happens? It's little compact and faster because it requires less internal wire. Can anybody tell me where is the less wire in the second network? Simple. See, D0 is the single wire coming, and I am taking this wire to upper PMOS and the same wire to bottom CMOS. So this is the one wire. For D1, this is the second wire. And for S and S common, third wire, and S bar and S bar, this is the fourth wire. What about these wires here? S and S, one wire, or no? Just try to see that. See, D1 and D1. Here D1 has only one wire, but here for D1 I have wire and it's complementary. You see there? Here I have need a bar, so I need to take the wire and invert to apply there. Can you see that? This wire will there, but then I'll have to put one more inverter here to apply D1. Similarly for the D0. Can you see this?
Yes.
So we'll say that this is little more compact, and because it is compact it needs less wire, so obviously the delay will be less in the network. So just try to see yourself when you go home, and we'll see that how this network can be efficient. So remember this, you only apply the inverting multiplexer by means of this tri-state buffer can be used to create such functions. And the bottom network is restoring logic again. The upper network is non-restoring logic.
Sir, the above one we know how to draw, but how to draw the below one we don't know, right? Like the above one is simple logic, we can apply and draw it. But the below one we don't know how we can draw.
Right. So good question. So again, come back here. So what we see here, there is a data input here. One. This is the tri-state inverter. We know that. Yes or no?
Yes, sir.
So just remember the circuit configuration. What we take, two bottom transistor, two up transistors, and we have on the top transistor we have a data input coming A, and this is enable and it's complementary to the middle two transistors. So this becomes one tri-state inverter. So we have done the same here. Instead
Yes,
of
sir.
A.
Yes, sir. For this one it is okay. See, there are many other design, right? This is not the only one. So for all the other design, we can apply the above one. That is easy. So for the below one, to make it as compact, is there any method to do that, or how we can do for other different designs?
Yeah.
Some
So, correct. So this is the one design, that this is the one method I just told you. This is the compound gate, and I told you that okay, why not use the tri-state logic to create this 2:1 mux. This is the one method. Another method, for instance, I want 4:1 mux. Can you just tell me how using tri-state logic you will create it? So this is the tri-state logic. Instead of transistor, I will just show the symbol now. This is no, I know that this is a symbol. One more time I will draw correctly. Yeah, I'm coming to an answer. So I know now this is the symbol of an inverter. Okay, this will have enable and this will have complementary. Obviously, even if I don't show, it is okay. I have shown only one signal, and this is the tri-state buffer. Okay, this is one. This is fine. This is enable signal. This is A, Y, A, and Y. Okay, so you know that. So your question, we want to know the different methods or any particular method. We know that how to construct using compound gates, but what about, let's say in this case we have used tri-state logic. So now I want to create 4:1 mux. How would I go?
first we have to draw the truth table, then get the equation.
Yeah,
After that,
this is the symbol for 2:1 mux. So D0, D1, and this is the output will be the bubbled output, because we have shown, that's why inverting one. So we know that output would be y equals to s bar D0 or s D1. So this is the logic function. Similarly, what about the 4 input one? Can we write y equals to
A bar
S0 S1 D0, then or S0 D1 or S0 D2 or S1 bar S0 bar D3. So this is the logic function, right?
yes, sir.
And you can just create the truth table also, but for 2:1 mux I got two pair of this tri-state logic. I know that this is how the single network, so I took two networks, one network, second network. So I will do 4 networks now. I will use 4 logics here. So see here what I am doing. I am using multiple 2 input multiplexers. So here is the logic diagram. So what I am doing is that this is one multiplexer, this is second multiplexer, and this is third multiplexer. So I am calling it using 2 input multiplexers. And how many 2 inputs mux I have? 3. 1, 2, and the 3. So how many data inputs I have? D0, D1, D2, D3. So the first mux is taking care of 2 inputs, second mux is getting care of 2 inputs, and this logic function that I have written here, that will be realized right through this diagram. So I have S0 and S1. So how many combinations I have? S0 and S1? Look, 4 combination. 1, 2, 3 and 4. So now I want to implement that. So I have used D0, D1, D2 and D3. Where are the tri-states? These blocks. 1, 2, 3 and 4. Right? Where is the enable signal? Here is the enable signal, and here is this complementary. Again, this is complementary, this is enable signal. This is enable signal, this is complementary. So for all that. And then I have this inverter 1. IN 1, IN 2, IN 3 IN4. So where is this inverter coming from? This is called decoding logic. Have you studied in undergraduate undergrads or grad studies decoder?
Yes, sir.
So you know how decoder works?
It has many inputs and output will be 2:2.
Yeah, yeah.
Like demons.
Right. So what is doing is that you have a 4 combination of this control now, H0 and S1 right here, H0 and S1. When H0 S1 are 0 accordingly a particular tristate will be selected, and that data from D0 to D3, any one of them at a time will appear at the output. So this is at the gate level. You can show them using the transistor level also. So this is how basically you see now. This mux also we use tristates. In this mux also we are using tristate. But the question again, can we use the compound gates to create this 4:1 mux? Yes, but that would be complex function, so many logic gates, large number of transistors, inefficient design. I repeat, inefficient design. And that would be again very important statement, non-restoring logic. It will work, but it may be degraded outputs will appear at the output, or speed will be less, it will not be compact. But this network using tristate, you can create that.
Sir, in the real time, are we going to design this as a physical engineer, or tool will take care of this internal things? We are just going to connect the things. How?
Yeah, good question. So see, there is a one term that is called IP, intellectual property. I have used these words before, right?
Yes.
So when you design library for your customer, you are working in at some company, your own company may have some IP already designed and included in the library, technology library. So when you are designing a chip at the block levels or the cell levels, you can directly ready-madely pick up that block. For instance, you can take this 4:1 mux block from the library which has been designed, which is your company's IP, right, from the library, and that IP, that particular cell IP is about 4:1 mux using tristates. So you can simply pick up that and use in your design. Okay.
Okay, sir.
So tristates approach requires.
Sir, let's say we don't, from the company we don't have anything. Let's say we are using an advanced tool. So will that advanced tool will take care of the things, or we should be having an library from the company?
Tool doesn't take care of your IPs. It's a technology library that in that you can include your IP. So technology library may come up with that IP, or as a designer you can design that IP and that insert that as a cell in that technology library and then use it for your designs.
Okay, that means we are only going to specify how it should be, not the tool.
Right. You are going to specify just the connection between the cells. Whatever the cells are already designed there, pre-designed, it's there.
Okay, sir.
Yeah. So now we see that tristate approach always requires enable signal for each tristate, and this enable should switch simultaneously to prevent contention. For instance, I have 4 enables. The enable signal is coming to these 4 of these tristates, and by somehow this enable signal to D0 gate comes 1 millisecond earlier than the rest of the 3. What will happen? The logic will misfunction. So that is called as contention. So when you apply a clock, when you have a clock in the circuit, that will generate enable and its complementary. These two, or just for a simplicity we'll say, when this enable will be generated, this signal should come to all the tristate exactly at the same time. A little mismatch would create a contention, just like a traffic jam, we say that. Now, all the circuits we are talking about, they are called as combinational circuits, using compound gates. Yes or no?
Yes, sir.
And what is the meaning of that? Combinational circuit means you have output and you have input, and the output depends on whatever available is at the input. So pass gate, we've seen that pass gate, right? Or inverter, or all the logic gates that we have seen, NOR, NAND. We know that whenever whatever comes at the input, whatever is there at the input, based on the logic switching that appears at the output, this is called a combinational circuit, and where output depends only on the current state of the input. But there is one more category that is called sequential circuits. So sequential circuit, it means you have a logic here, and this is, let's say, sequential one. So you have input and then you have output here. So whatever the output depends on the input, no problem, but also what was the logic that was already stored in the logic, output will also depend on that, whatever the logic was already stored. So that's why we call it as a memory cell. So output depends on both current state, whatever is having at the input, and what was previously at the input. So that gets locked here in the sequential cases. So we call it it has a memory. We say that such circuit have a memory. So two examples, latches and flip-flops. So we'll see that what is the meaning of that. So again, in combinational circuits, output depends on only the current state. Whatever is the current available data, output will reflect that. But in sequential, output depends on both current and what was the previous state of the input. So we'll see that what is the working exactly. So first case is the D-latch. So what is the D-latch? We take two input mux. We know that this is the mux now looks like, and we then take two inverters. Look, here is the inverter 1, this is inverter 2, and we take one mux, and we know that what is the mux, how to implement mux. Mux is implemented by pass gate. We know that we can use a transmission gate to implement the mux. So now look at this circuit. This mux has clock. So this is called as enable signal. So when I say clock, I assume the circuit will have clock bar. When I say enable, I assume the circuit will have enable bar. It's always will have its complementary. So look at this circuit, how it's looking that. I give you 1 minute to just have a look at this circuit diagram and the logic diagram and the block diagram, and just try to understand before I explain you how this circuit is working. I am going to explain you, but I just give you a moment to take a look at this circuit, how the circuit will work. So now you have a clock. Clock means is the special enable signal. Again, somebody will ask you what is the difference between combinational and sequential logic. You can simply say a combinational circuit doesn't have clock, or combinational circuit doesn't have memory. So what I am doing here is that this mux I am building using two pairs of transmission gate. This is single pair and this is the second pair. The inverters I kept same, right? And what I am doing again, see how the circuit will work now. We'll see that. So I have this clock here in the block diagram. Inside this block, I know that this mux is a two pair of pass gates I have taken, NMOS and PMOS in parallel. So when I apply clock here, I have its complementary, and I have applied clock here to the PMOS and it's complementary to the NMOS. See, these two clocks are reverse here. Here to the NMOS I am having clock, and to the PMOS I am having the complementary. But here in this pass gate I am giving complementary to the PMOS and normal to the NMOS. It's just to make the switch on and off one at a time. We'll see that in this bottom network. So let's see how this circuit will work. When the clock is 1, let's say here is your signal. This clock is 1, so I am enabling the network. What happens when the clock is 1? This latch is called as D latch. D stands for data. So data could be logic 0 or logic 1. So I say when the clock is 1, the latch is transparent. It means anything can pass through this. So I would say when the latch clock is 1, it means this guy is 0, this is 1, this guy is 0. So I know, obviously I can see that the D clock is 1 gets connected or it appears at the output. Simply. Similarly, I have inverter here. So if D was 0 or 1, here comes 0 or 1. Obviously this D also going through the inverter. So it's a Q bar. It means whatever the Q is, it's opposite to that. Just complementary. And now this signal is here, but now this switch is open because clock is 1. Because of this combination 1 0 1 0 here. So I see this switch is open. So when clock is 1, D connects to Q. So I say that latch is transparent. It means data can pass inside. But when clock falls to 0, D gets open. Why? Because again I apply this is 0, then this is 1, then this is 0 and this is 1. I will see which pass gate is switched on and which pass gate is switched off. So here is that circuit. So when clock is 0, the Q remains at a previous state. So whatever in the first cycle when clock was 1, whatever the D was, that came at the output and it remained like that when the clock went 0. And again the Q bar was obviously the complementary of Q. But now there is a feedback path. So again I will say it's coming back to the same. So it's the previous state, nothing but. Okay. From the timing diagram, how can we understand this? This is called as logic 0. This is logic 1. So clock is 0 here. But now here at time t, I have clock became 1. So what was the 0? D there? D is 0. And when clock became 1, D is 1. And what is the Q then? Q was 0 initially, but as soon as clock became 1, Q got the value of D. Look, D is here 1, so Q also is following the D. So output is following the D. Now D is going 0, so Q is also following the D because latch is transparent and it continues like this. Then again up till here I am seeing that Q is following the D. But here clock went from 1 to low, from 1 to 0. So at this stage D is 0, so Q remained in the previous state. Again I made logic 1 at the D, so Q should follow it. But why is it not following? It is remaining in the present state, previous state. Why? Because clock is 0. So these two circuits. Did you understand this? Very simple.
So how can we draw the second figure by using the transmission gates?
You mean this figure?
Second figure.
This is figure 1. Is it?
Yes.
This is figure 2.
Yes.
Which figure you are talking about?
Second figure.
So this one, right?
Yes, yes.
Okay, and what is your question?
How can we draw that circuit?
How can we draw this circuit? We know that you have how many pairs of transmission gates?
2 pairs.
2 pairs. Good. So we have 2 options. Use the compound gates. We know that how to draw the transmission gate.
Okay, this is a two input multiplexer, so we are using two transmission gates.
Yes, correct. Yeah, you are using two transmission gates, simple. Now how to create the transmission gates, you know that. Okay, I will tell you later. Let me complete this, and we will come about how to implement this circuit. Okay.
Okay.
Yeah. For a moment, we are just understanding the operation. What is D-latch? How it works. This. Let us understand this basic principle of operation first, and then we'll see how to implement this circuit. This is your question, right? How we implement this circuit.
Yes.
Right? Yeah, we'll see that in later. So, anybody has a doubt how this circuit is working? We know that two input multiplexer we have to use and two inverters. So this is two input multiplexer. I have this and inverters, and then I know that how to implement mux. Mux can be implemented using transmission gate. So this is the two transmission gate or pass gates I am using. Anybody has a doubt on the working principle of this circuit?
Sir, once again explain the waveform, sir.
Yeah, waveform again. When the clock is 1, from 0 to 1, it goes 0 to 1 here. So we say that latch is enabled or latch is transparent. It means data can go inside the circuit, and obviously if it goes, it appears at the output. So we say that when it goes transition from 0 to 1, D is 0, and at this particular time D is 1 now, right? So Q is 0. At that time Q is 0, but when the clock is 1, clock is enabling here, very simple, and D is here 1, so at that time Q became 1, because at this moment I found that the circuit found that the clock is 1 now. So Q became 1. So now it is following the data. It is following the data. Now data went down. It is again following the data, and data remains 0. Q is following the data, but at this particular time clock went down. So data is 0 and again went 1, but Q will remain in the previous state, because latch is opaque. Transparent means it allows data to enter. Opaque means it doesn't allow the data to enter based on the gate. This is clock is the gate. It opens the gate or closes the gate.
It depends on circuit, sir.
Which it depends on the circuit. We are having circuit, waveform, switch diagram, everything here. Understood?
Yes, sir.
This is very important and very simple. Don't get confused. Just see these 3-4 lines. See this waveform and see this logic diagram. See this circuit diagram. This is the switch diagram. Just to help you understand more in a very simple way how the switches and closed and all. So now this is called as level sensitive latch. What is level sensitive? Level sensitive means when the clock goes from 0 to 1, or when the clock goes from 1 to 0. This is called as rising edge. These are very important words that will come here. This is called as falling edge. Why I am showing this triangle? Why I am not showing this one like this or like this? This is like 0 to 1 and 1 to 0.
Delay.
Yeah, there is delay. So it means when the signal goes from logic 0 to logic 1, I am having certain delay here, right? Having certain delay. So this is called as, if you remember, rise time in control system or even in the digital logic. T delay, you are right? Again, for the falling I have some delay. So this is the ideal case actually, right? In practical situation, you will always have some delay, maybe 1 nanosecond or something like that. Okay? So level sensitive latch, the state of the output is depends on the level of the clock signal. Means whatever the output 0 or logic 1, that depends on what is the clock, if it is 1 or 0. So output goes that. And this is called as positive level sensitive latch. Why is positive level sensitive? Because you see it's transitioning from 0 to 1. So this is the level that we are catching at the output. That's why it's called as, it's acting, the circuit is responding to the positive level sensitive latch. And this is happening because of the way I have designed the control inputs here. What is the control input? Here, clock to the NMOS, it's complementary to the PMOS. But in this bottom pass transistors, clock is to the PMOS and its complementary goes to the NMOS, just opposite to this behavior. What if I just change this logic here? So this logic comes to this pass gate and this logic comes to this pass gate. Then it will be called as, this circuit will respond to a negative level, it will be called as negative level sensitive latch. So this circuit is an exercise for you. You will see that it responds when the level falls from 1 to 0. So we'll say that this latch is responding to the negative level latch, negative level of the clocks, and the latch is called negative level sensitive latch. Try do it when you go home. Just reverse the logic and you will see that what comes when D comes to Q depending on the clock condition. So just invert the controls, okay? One more circuit and the interview question, what is D latch? First question. And what is the difference between D latch and flip flop? So does the previous circuit has a memory?
Yes, sir.
Because which is holding on to that value, right? Even the input changed here, it held on to that value, right? It knew what was the previous state, right? And it is a symbol.
Sir.
See, symbol is simple latch, data input, output, and the control. Simply say clock. Now what is flip flop? Flip flop is, take one negative sensitive latch and one positive sensitive latch, D latch. D is data latch. Now what is negative sensitive latch and what is positive sensitive latch? One latch will respond when clock transitions from 0 to 1, and one latch responds when clock transitions from 1 to 0. This is how the behavior is. So what I do here, this is my input, this is my output, this is my latch 1, this is my latch 2. Now again, coming to the question of Sangeeta, latch is implemented by MUX and MUX is implemented by pass gate, and pass gate is implemented by compound transistors, pull up and pull down network. Sorry, the MUX is implemented by compound network, pull up and pull up transistor. Pass gate, we know that how we implement it. It is the pass gate, A and B, and this is G, this is GB. Are you following me? We'll see that circuit implementation. Do you agree with me? We'll see that how the circuit will take place. Okay, so now latch 1. So output of the latch 1 I will call it as a master output, QM. Output of the another latch I will simply call it Q. And look how I am applying the clock. Clock comes here, that goes straight to the second latch, and inverted version, obviously the clock bar goes to the first latch. So I combine two latches, one negative sensitive and one positive sensitive, and here is the circuit. So this circuit, if you see that, I break it into two sections. So this is nothing but D latch and this is D latch. Can you tell me which latch, if the two latches are exactly same or little difference somewhere?
Difference is there, sir.
Which difference?
In the first one, NMOS is connected to clock bar. In the second one, NMOS is connected to clock.
Correct. So you see this logic we are applying, the clock logic, that is different, right? And here also is just complementary to what we are doing in the first latch. So that's why we will say that one latch will respond to negative clock transition, one latch will respond to the positive clock transitions, right? And when that latches responds to this transition from 0 to 1 or 1 to 0 of the clock signals, we call it as a edge triggered flip-flop, because edge, this is called edge, this arrow indicated by arrow. So when you do the RTL coding and when you do the model sim, when you use the compiler, right, then you will have a waveforms like we are showing here. These waveforms will come to you, these waveforms. So you will show clock, then input and the output of the circuits, and you have to interpret these waveforms at what transition of the clocks, whether it's passing from 0 to 1 or 1 to 0, how the data input is changing and how the output of the circuit is changing. Okay, so first latch is called as master and second is called as a slave, because slave will follow the order or take the orders from the master. So we'll see that in a moment how this circuit will work now. So again, this is the logic diagram. So let's understand first when the clock is low. Clock is low means right over here. We fail from logic 1 to logic 0. This is 1, this is 0. So what happens? Again, we can analyze simply. There are 4 pass gates. There are 4 pass gates. So when we apply clock equal to 0, easily we can understand which pass gate will be on and which pass gate will be off. So when we say that when the clock is low, the first D latch, we call it as a master, and it is a negative level sensitive latch. Its output, which is the master output, will follow the input D. So D will come here through, of course, at the inverted level, because there is an inverter here. There is an inverter here. And of course this QM cannot go back because this switch is open. But now this switch is also open. So the slave is disconnected from the master. Slave is not responding or following anything coming from the master. This circuit is 2 different circuits. Okay? Whatever the value, yeah. And what will be the output of Q at the slave? We don't know. What was the previous, it would stay in that state because this is completely disconnected from the master, right? But we for sure we know that the data will come at the QM, and the data would 0 or 1 will appear as 0 or 1. So look at this. When the clock falls to 0, the D is at the level 0 and the Q is shown to be at the level 1. Q is this, not the QM. Okay, in the waveform we are showing this 1. Okay, so it doesn't matter what is there, it remains in the previous state. But now we'll see what happens when the clock becomes 1. Here, when the clock will become 1, we'll see here, when the clock transitions from 0 to 1, the master latch will get latched. Opaque means latch. So not here, look here now. So D got open, the clock is 1, and what was transferred before, what was there in the D, it got in the previous clock, it got here and it remained there. But now these 2 transmission gates got opened and closed. This got closed here, this got open. So this QM, the output of the master, is getting connected to the Q. So clock became 1 at that time. D is 1, and you see now the clock is 1, D is 1, so output is following the input data right here. So clock is 1, it failed 0, but Q is not falling 0. Q it is in the it's in the previous state. Are you following me?
Yes, sir.
Right? So why it's remain there? Because D is falling to 0, but switch is open, right? So nothing is coming. The slave is just taking the order from what was at the QM. So this is how the slave became transparent, and it passed the stored master QM value to the output latch, final output, and the D input got blocked from affecting this final output Q because master got disconnected from the D input right here. Very simple. So we say that when the clock will transition from 1 to 0, 1 to 0 again, it is 0, the slave latch will hold the previous state, and look here it's coming, but now the slave got disconnected and the master is got ready again to whatever the D is here, it start receiving the D value. So in the summary we say that this flip-flop, master slave flip-flop, copy the value of data D to the Q, final Q, D to Q, right, based on the sampling of the switches, and we say that it copies that data on the rising edge of the clock. So this is the principle of operation for the flip-flop. This flip-flop is called as positively age triggered flip-flop. Why? Because we see that the data D comes to the final Q only at the D equals clock transition from 0 to 1. Assignment for you would be create the circuit diagrams and the timing diagram when data D goes to Q at the falling edge of the clock from 1 to 0. Okay, so this is how we see that what is the D flip-flop. This is basically a D flip-flop. D latch is nothing but the D flip-flop, or we also call it as D register. Why we call it as a register? Because it stores the value, or we can also call it as a flip-flop, and name, special name would be master slave flip-flop. So that was all for today, and we'll see that some other question. Yeah, just one last slide that I want to. So if we can see that if we again, just like in the previous class, previous slides, if you just reverse the polarities of these clocks, whatever you see CLK bar goes to NMOS, so create another circuit where CLK goes to NMOS, and just every pass get like that. Then we'll see that this circuit works as a negative age triggered flip-flop, 1 to 0. This logic diagrams, this switch diagrams will change then. So the collection of such D flip-flops sharing a common clock is called as a register, and register is just to store one bit of information, and when the clock comes this keeps on changing. Now one important point, when you design, when you write a code, you want to generate two clocks in your code. These clocks, now you see I am not writing CLK here and CLK bar. What I am writing, phi 1 bar, phi 2 bar. Does it make any difference? No. I can also write enable bar. I have told you that before, right?
Sir, this means we are supplying different clock now.
Clock will be generated inside the cell. Yeah, you have to design a clock circuit also. Clock circuit that will generate a clock, and then you have to just again put some inverter logic, then that will generate the opposite of that. and then these are the two clocks coming here. Is that your question?
No,
Yeah.
sir. Earlier it was difference was only clock and clock bar. Now it is something 5152. That means both are different clock itself, right?
Yeah. It's a single clock circuit with two opposite, with its complementary function also.
But now the one which you have, it is there in the diagram. What is that? I don't know. Psi one is it?
Yeah,
No, no,
phi
no.
1, you can say phi 1 or psi 1.
Yeah, phi one and phi two. That means different signals. Not only inverter. There are
Ah, yes,
four.
yes, yes, yes,
Four.
yes. There are two different signals, 1 and 2. Yeah. So you see now they are non-overlapping. Non-overlapping means when it is 1, when it is complementary. When it is 0, it is 1. Again, when it is 1, it must be 0. What if you have like, I'm drawing the ideal one, and then this is okay, but what if you have like, this is your clock, something like this, so it's logic high, right? You have logic 0, here is logic 0, so it's little overlapping. So that particular point is called as clock skew. In RTL designer or physical designer, when you write compiler, when you use compiler, when you do the synthesis of this circuit, synthesis is the process of connecting the inputs, outputs, and defining the clock. So once you define it in the code, then synthesis, the tool will automatically use the logic gates, flip-flops, everything, and connect them together according to your function. So it means if the one flip-flop, if this situation clock skew occurs, it means the flip-flops and these pass gates will not trigger simultaneously at the same time, exactly at the same time. There will be some mismatch. One will trigger earlier than the other. So obviously circuit will not work as expected. So in the industrial design, your effort as an engineer, as a designer, to to pay attention on the timing based simulations. You have to understand a lot of waveforms and the timings, and you have to catch the whole time problems, which is nothing but the, is there an overlap between the clocks, are the switches happening at the same time. It's not that I have a trained transistors as the switches, 5 are switching the way I want, and other 5 are switching later or earlier than the previous 5. So that's not the good design, right? So how to avoid this? So again, you have to generate two individual clocks, as Naren said, and then distribute them as in a non-overlapping fashion, so that they will trigger these switches on and off at a proper timing, right? So as long as these clocks will never overlap, at least one of the latch, master and slave, you have two now. So this circuit will function precisely as long as the switching is non-overlapping. What we want ultimately this circuit to work best, at a one time only one slave or master, one latch is switched on and off. When one latch is switched on, we have seen that other is off. Look here, this is off, and when other is on, first one is off. So this is what we want. So that's all for now, and you have any questions, let me know.
Sir, D latch, how many bits it is storing?
1 bit.
Flip flop?
Again 1 bit.
Hmm.
Now what is the question between D latch and flip flop? That is the interview question that you have
One
to
is
tell.
edge triggered and another is level triggered.
Good. Yeah. Any other difference?
Sir, sorry, what is the answer?
Now she said, what? Can you repeat the answer again?
Flip flops are edge triggered and latches are level triggered.
And any significance
One
or
question, sir.
yeah, we will come to your question. Just a moment. Let her complete. And any significance about that? What we mean by level trigger and edge trigger? We know that we just saw. But what? Okay, what happens because of that, and why then they are different? because of this.
No, the question is difference between flip-flop and D-latch, is it?
Yeah, that's my question, and she
Okay,
answered
okay.
flip flops are edge triggered and latches are level triggered. So I said okay, and I want to know from you people that please elaborate. Can you tell me like okay, they are latches are level and flip flops are edge triggered, but because of that, what we are understanding and what's the meaning of that?
In the edge trigger, we use clock.
In the D latch also we have a clock.
Basically, what I personally think is we generally use flip-flops just because these are, I think, most of the clock circuits that we see in today's SOCs or anywhere are based on the transitions, not based on the levels. So that is the reason why flip-flops are used, and flip-flops may operate at higher frequencies, but latches may or may not, I'm not sure, may not operate at high frequencies. I personally think that's the reason why flip-flops are used over latches.
Okay, so any other anybody else who would want to answer?
Flip-flop will use, can use only one, either, positive rising or negative or falling edge.
Yeah, she said that it's a edge trigger, so it could be positive or negative. We've seen that in the master slave. Slave is operating at the falling edge, and the master is operating at the leading edge or rising edge. So yeah, so think about that. I'm gonna answer you in the next session, but think this is important question they will ask you during the interview. Okay, so we stop here. Thank you very much. Any other question, or you have any other non-relevant question linked to the not linked to the slides or my teaching, but some other
Sir, this if you are using clock, then it is also chances that it is a level trigger. I believe that if you are using clock, then always it is an edge trigger.
no, it could be level trigger also. Why not?
Gated latch is the
What?
gated latch is also there, right?
I am not able to hear.
So latch is also having gate.
Yes.
Clock.
Yeah.
So both are same.
Yeah, but there is one fundamental difference. That is my question is I'm going to answer it, but I want you to think first, and of course I'm going to give you because we can see that in the latch when the clock is enabled we say that data was reaching to Q, D was connecting to Q. When the clock is disabled we said that it just latch means what? It's just a door. When the key was inserted in the door got open and the person came in. When the key was not there, the door got locked and the person could not get in. That was the simple operation of the D latch. It became open and close. It was just a door. What was flip flop? For the rising edge and the falling edge, not the level. We use these words and we use this for the rising edge and the falling edge. We saw that instead of one latch, we use two latches along with two inverters, and we say that at a time only one was getting a latch was getting closed. It means one door was getting closed and it was letting the guest enter inside the house. Okay, and at the other instance of time when the clock was 0 or 1 at the following edge, another door got open or closed. So two doors, one door was open at a time. When one door is open, another is closed, and when another door is open, first one is closed, and based on that we allowed the guest to enter and transfer to next room or something like that. Think in this point of view.
Yes, sir. I understood that.
So think I'm going to answer you that.
Question, sir.
Yeah.
Uh, um, why why would anyone use the flip flop instead of latches? Even the flip flops require double the space of latch to store any element, but the latch itself uses half the space of the flip flop to for storing any for storing uh, used as a memory. So my question is, why would someone prefer latch, even though it's okay, or even though the latch occupy less space than flip flop?
Yeah, that's the question. That is what the answer is there only. This again the same. This is another way of asking the question. So the difference between latch and flip flop is the answer. That's what I want to know from you people, and then I will explain you. First, I want you to reach to the answer. So think about that. Next session, we will see what's the fundamental difference between these two, and just like you use, why not use latch instead of flip flop? If we can save space, we have number of less gates and so on, and also any other point we'll cover link to that. But I hope you are clear with this. What is level sensitive, what is edge triggering and level triggering.
Yes.
Any other point or some other
One last
general?
question, sir.
Hmm.
In making flip flop, we use two positives, one positive sensitive D-latch and a negative sensitive D-latch, right?
Hmm.
But the output of the Q bar of the positive sensitive D-latch is connected to the Q of the input D of the negative sensitive D-latch. Directly in normal blocks, what we basically do is we directly connect the output of the what do you say that? Yeah, negative, positive sensitive positive sensitive output to the negative sensitive of the other latch. In this case, it is connecting the Q bar, not the Q. So how does that work? That's the question.
Wait, can you see my slides?
Yes.
Maybe you have to tell me.
Yeah. In this, basically, whatever the output that we are getting from the left hand side is the Q bar, correct? But in normally when we perform master and slave operation, when we draw it in a master and slave way, we directly connect the Q to the input of the other to the slave, the Q to the other slave, right? But not the Q bar. I hope you're getting what I'm trying to say.
Anybody else got what he's saying?
But I think other way of JK flip flop or some other flip flop, he might be explaining that other method how you construct the flip flop, but it is not there.
Basically, can you draw the master block, sir, of the D latch?
You want to see the D latch?
Yeah, basically, yeah. If you can go a little above. No, not the
This
below one,
one?
the below slide. No, no, one more slide. Yeah, in this you can see here the in the upper circuit, in the upper one. Yeah, there is a master and there is a slave, correct?
There is no
Um,
master and slave here.
oh, sorry. In the 13th slide, please go to the 13th slide.
13. Okay.
Yeah, in that you have the upper circuit. If you can see, there will be a master and a slave, correct, sir? For flip flop to operate,
Just a minute.
for a flip flop to operate as for to make a flip flop, we need a master latch and a, slave latch, correct?
Yeah, yeah.
So the master's latch Q is connected to the slave's input, correct? Q, not the Q bar.
Master's output is connected to the slave's input.
Yeah, correct. The Q, not the Q bar. Here the Q bar is connected.
uh, Q bar is connected, yeah, where Q bar is connected where? Here to the slave when the clock is
Correct.
1. Yeah, go ahead.
But what we see is the master's Q, not the Q bar. Q is connected to the slave's input when we are drawing.
You mean this feedback in the bottom?
Uh, can you show me? Yeah. Yeah, this one. The Q should be connected, right? Basically, in the in the master's latch output, there will be Q and the Q bar, correct? The Q will be connected to the input of the slave, not the Q bar.
No, no, it's
When
not
we
a
are
Q bar. What we are saying is that, let's say, once again, we are just trying to explain the operation in a very simple. Don't get confused. We have clock 0 and clock is equal to 1. When clock is 0, either master or slave will be switched on. And when clock is 1, again the same case. So we are saying for the first case, here this diagram, when the clock is 0, your master is active. So whatever the data is D, that goes to the output. And output is of master is indicated by QM bar. Why we show bar? Because there is an inverter here. So if D was 0, 1 comes here. If D was 1, 0 comes here. Just try to understand. Just let me finish this.
Sir, it should be indicated by D bar, no? Why Q?
No,
Okay,
it's
Q is equal to D bar. Q, okay.
yeah, you can just, this is
Yeah,
just
yeah.
the way we write. And
Correct.
at the same, in the same cycle, we are seeing that slave is completely disconnected from the master. So it's not taking orders from master. That's why we call it as slave. And Q was whatever the state was before. We don't know, because we started analyzing from this time t equal to t1. We don't know what was the previous state. But now clock becomes 1 from 0 to 1. So in that case, we know that the D got disconnected from the master. But now this pass gate got active. So the slave started receiving, this door is open now. Switch is closed means this door is open, and QM bar, the master's output, is getting to Q. So now we say that the D, what was D before, that was in the first cycle, it was transferred to QM bar, and then in the next cycle, in the next transition, it came at the output. This is the simple way of understanding things. Again, when the clock becomes
yes.
0, the same master is ready to take the input from D. Nothing else.
Yeah, sir, I understood that operation, but
Hmm.
uh, can I use a pointer, sir, for a minute to just
Yeah, yeah, yeah.
point where?
Wait. I give you
Sir, I
access.
think what I understood as stated earlier is maybe referring some other logic which we have already seen. Maybe JK flip flop. That is what Bilal might be thinking
No,
of.
no, I'll just point it one. If I
One
can.
second. I give you
uh,
the. I give you the access. Wait. Can you see now?
Yeah.
You can use the pointer.
I'll. Yeah. 1 minute. In this we have QM, right? But in here we have QM bar. That's what.
Okay. That's what you are explaining me.
Correct, correct, correct.
Okay. No. Just imagine. Just understand that there is something missing here. I should have shown this QM. In the symbol, I have shown QM and Q just to identify two different outputs. Here, I have shown you QM bar and Q. I can write QM also here. No problem.
Yeah, so basically what I'm trying to say here is we have two latches, correct? Okay. Are we interconnecting it like this and then giving it the output, or else are we connecting it like this? This is the clock.
And what are these two lines you are showing?
Yeah, this is the Q. Sorry, this is the Q and this is the Q bar, correct? For a latch. Okay, I have
Yeah,
mistakenly
yeah, yeah,
connected
you are
this
right.
one.
Yes, whenever you show Q, you can always show, as I said earlier also, whenever you have a particular line, you can always show its complementary function. So if it's a Q, it will have Q bar. Flip flop will have
Yeah,
always
so
complementary output.
what is connected on the slave side? The Q or the Q bar? That's the question.
Ah, okay, okay. So it's a Q. Is
Okay,
simply the output
then
what that comes here. We'll say that. Yeah.
it's Q, correct.
Yeah,
Then
like Naren said,
why
you
are
can
we?
also write the y here, and y equals to d bar something. You can always say y, and y gets connected to q. Y gets connected to
Okay,
slave. Yeah, just don't misinterpret that. You can write anything there.
okay, okay.
Yeah.
Thank you.
Okay. So, any other discussion you want to make, or we continue next time? So if there is no other question or point, we'll see next time. So I hope you got this. Next time I'll explain where to use D-latch, where to use flip-flop, and what are the, from the design point of view, how we can, what are the advantages and what are the disadvantages. But obviously somebody said D-latch just one cell. We have two latches needed to create a master and slave, then why not? We'll see that those points here. Okay, thank you.
Thank you, sir.